So good evening all guys. Good evening. So hope my voice is audible to everyone. Is it audible? What about my screen? Is my screen visible to everyone? Thank you all guys. Okay, yes, so welcome back to 13th contact session of our Big Data Systems course. So yes, guys, I am really excited to be with you today. So before we jump in, so let's take a moment for some inspirations, guys. So still we have 1 minute of time. Let me take one inspirational thought. So this is said by a brilliant mind. Okay. The only way to do great work is to love what you do. My dear friends, so you are here mastering big data and a field that is constantly evolving and shaping the future. So keep that passion burning and let's conquer this material together, guys. So today is a heavy duty session. So where we will conclude our discussions on core storage concept like block and file storage. So now we are diving deeper into the fascinating architecture of DynamoDB and then pivot to introduce the powerhouse of big data computation, that is Apache Spark. So we have a lot of ground to cover, guys. So let's maintain this high energy and focus. Okay. So are you all ready for today's session? Can I get quick confirmation on chat box? Are you all ready? So can I get ready message on chat box in the evening? Yes. So I want the message from all guys. You all ready, right? So look at my energy, guys. So you have to see your message has to show your energy. Okay, good guys. So let me share my screen. So meanwhile, I'll do one thing. So I'm going to start meeting on mobile also. Once again, guys. Yeah. So where I'm getting chart in mobile. Give me 1 second, guys. I don't know where I'm getting message here. Yeah. So if I'm getting any messages, I'll get here. Okay. Yes, guys. So let us start with today's session. So let me share my screen. So where is the chat box here? Okay. Yeah. Guys, let's quickly recap the topics for today. Guys, we are wrapping up our storage unit. So we touch upon object storage. So in the previous class, and also we have touched upon file storage with elastic file system. So these two concepts we have completed in the previous session. And we have to complete so block storage and also databases. Okay, so block storage is nothing but specifically so elastic block storage. So we have to talk about elastic block storage, and we transition into databases that is focusing on key value store. That key value store is using this DynamoDB. Okay, so let's zoom in on block storage, guys. So which is what EBS is all about. Okay, so look at the second slide. See, the first point says it is block storage for EC2 instance that can be attached and detached anywhere, anytime. Okay, so think of it like a virtual hard drive for your EC2 virtual machine. Okay, so it is not inside the machine. So it is a network attached resource. So this detachment capability is a very important point for durability. Okay, so if your EC2 instance crashes, your EBS volume remains safe. So ready to be attached to another instance. Understanding my point? Next is, the second point is, it provides a volume as a collection of network attached blocks that are exposed as a disk. So this is the second point I'm talking now. Guys, when you format 1 TB EBS, okay, 1 TB EBS volume on your EC2. So on your EC2, so it looks and acts exactly like a physical 1 TB disk. Okay, the operating system sees a raw disk and it does not know, or it does not care that the block are actually traveling over a network to a distributed storage cluster. Understanding my point, guys? And depending on performance or cost, so one can opt for HDD backed or SSD backed volumes. So this is the key for cost optimization. So this is the main key for cost optimization. Okay. So if you have a log archive that you access once a month, so you would choose a cheaper magnetic HDD backed volume. If you are running a high transactional relational database, you must choose a high performance SSD backed volume, like a provisioned IOPS STD. Okay, IOPS SSD. So finally, EBS volumes are durable and replicated within availability zone. So guys, durability is the promise that your data won't be lost. Okay, so AWS achieves this synchronously, replicating your data multiple times within a single available zone. But remember the caveat, guys. Okay, so cannot move a volume to another AZ without a snapshot. The meaning of this is, if the entire AZ fails, this tells you EBS is AZ scoped, not global. So got it, my friends? So that sets the stage for our comparison. And yes, that is very, very important one. Okay, let's look at how EBS stacks up against EFS on the next slide. See, here we have taken the comparison. This is the classic question in system design, guys. So when do you use block storage and when do you use file storage? This is one of the beautiful question you are going to get every time. So let's break it down point by point, looking at the core differences. So what is the first difference? See, first under EBS. So I'm taking EBS first and then I will go to EFS. See, look at here. So it can be only accessed by one instance at a time. One instance at a time. Guys, this is the fundamental constraints of block storage. Remember this. So it is a single tenant disk. So just like your physical hard drive, guys. So it can only be plugged into one computer at a time. Okay. And also, guys, it offers steady, predictable performance for a single instance use case. See, for that single instance, you get phenomenal performance. Phenomenal performance means it is up to 4 GB per second, 64 TB, 260K IOPS, and sub-milliseconds latency per volume. Guys, this makes it ideal for IO intensive applications like relational databases or OLAP engines. So this is a very important use case to note down, guys. And also it have multiple performance per cost option. So which we just discussed, right? So HDD versus SDD. So in previous session is HDD versus SSD. Same thing. Okay. And it is cheaper than EFS per volume, but only for one instance. So effectively more expensive. If multiple instances need the same data, means it is a little bit expensive. Okay. So now let us look at EFS. Guys, it is like distributed multi-user network file system. Okay. Think of your traditional network file system. So what was that? Network file system. Traditional network file system. Guys, it is, see, I'm comparing with network file system. So this is infinitely scalable. It uses the standard file level protocol. So multiple servers can mount and read or write to the same file system simultaneously. And guys, it provides scalable access across many users with decent performance. Guys, the key here is many users and scalable. So this many users and scalable is the key points you have to understand. The performance is decent, but often not as low latency as EBS for a single instance. Okay, so it costs more per GB, but is shaped by multiple instances. So turns out cheaper for cost sensitive shared storage applications. Guys, this is an economic flip side, guys. If 10 application servers, so let me take the example. If 10 application server, need to share 100 GB repository, then EFS is the cheaper and simpler architectural choice. So despite its higher per GB price. So let me take one analogy to explain on this, guys. You just think of EBS as a sports car engine. Okay, usually what, guys? So sports car engine will be having high performance, one driver, correct? No? Are you getting my point? So think of EFS as a public bus system. It is scalable, many users, but the overall trip time might be longer. That is the difference between EFS and also EBS. So with that comparison of EBS and EFS complete, so we are ready to move into the database side of our big data system. So specifically, so we are talking about key value NoSQL stores. So let me see, guys. So till here, everything is clear. EFS and EBS. So can I get quick confirmation on chat box? So once it is clear, can I get confirmation? Is this clear? What is EFS? What is EBS? Okay. Guys, now, see now transition into database segment of our storage discussion. So which as the slide shows here, that is a key value DynamoDB. Key value DynamoDB. Guys, we have already covered object, right? So we have covered file concept. We have covered block storage concept. The word of big data is heavily reliant on NoSQL databases. And DynamoDB is arguably the most famous example of a production scale high availability key value store. Okay, so make a note of this, guys. So when we talk about DynamoDB, so we are talking about two things. What are the two things we are talking about? The original DynamoDB paper. So this is given here. The original DynamoDB paper. So this reference is given. You just go through this. Guys, this is Amazon's groundbreaking paper from 2007. Okay, so which describes the design principle of the system they built for their entire e-commerce platform. So it is foundational text in distributed systems. You can find the link on this slide, guys. See, this is the link. You just click on this link. So it will direct you people to that particular paper. This is one thing is very, very important. And another one is the managed service DynamoDB. Okay, so this is the commercial product offered by AWS. So which implements many of the concept from the original Dynamo paper. Alongside other systems like Cassandra also given here. So the concept we will discuss like consistent hashing, vector clocks, and N bar, R bar, W quorums are core to understanding all distributed key value store, including Cassandra and also React. Okay, so look at the next slide. So I'm showing you the what applications. So next onwards, guys, next few slides. So we are going to step into the shoes of distributed system engineer and understand why these systems were designed the way they were. So this is a very important section for your theoretical understanding of big data system. So let's first look at the what unique set of requirements that drove Amazon to design Dynamo in the first place. Okay, so here we have mentioned applications and also requirement. My dear students, why did Amazon create Dynamo? That is the first question I will ask to each and everyone. Guys, they had a specific set of needs that traditional relational databases could not meet at their scale. Okay, and look at the application listed here. So what is the first one we have listed here? Bestseller list, shopping carts, customer preferences, session management, sales rank, and product catalog. Guys, what do all of these have in common? Okay, guys, they need extremely high availability and low latency. Okay, high availability and low latency. And they often don't require complex relationship. Understanding my point? So this led to the following requirement. What are those following requirements? See, requirement I have listed here. So requirements I have listed here. So the very first one is query. Okay, guys, they needed no relational queries. Just a simple key-based object retrieval with object size less than 1 MB. So for example, so let me take one small example to explain on this. Guys, get the shopping cart object for user ID. Let me write here. So user ID 123. Simply key lookup, no join, no complex SQL. So this simple model drastically improves performance. Okay. And second point is ACID. So we all know the relational databases, 4 pillars, right? ACID property. Okay. What is that ACID property? Is nothing but atomicity, consistency, isolation, and durability. But remember the CAP theorem. So DynamoDB always prioritizes availability over consistency. Okay, AP. Availability over, sorry, consistency, AC. Okay, so guys, here, see, transactions always reduces availability, no strict consistency requirement. So if a user is updating their shopping cart, Amazon wants that right to succeed always. So even if the node is down, therefore, there is no strict consistency requirement. So we will see how they manage this eventual inconsistency shortly. Okay. And the next point what we have to discuss here is efficiency. Guys, they had to achieve this on commodity hardware. So this is the core of big data. Okay. So it also required strict low latency at 99.9 percentile. So this means out of, see, 999 out of 1000 requests must be fast. So this is a massive engineering challenge and forces a crucial trade-offs between performance, cost, availability, and durability. Okay. So the next slide details the what design thinking that emerged from these requirements. Let's move on, guys. Design considerations. Guys, building on the requirement from the last slide, let's look at the what core design decision Dynamo made to achieve its goal. The first one is most critical one. Guys, consideration is that the system must be highly available for writes. My dear friends, so imagine trying to what update your shopping cart before checkout and the system fails. That's a what lost sale, right? So Dynamo ensures you can update your shopping cart even on network partition. So this is called as pure availability in CAP theorem. Understanding my point, guys? So this is called as pure availability in CAP theorem. But if writes are always allowed, so what happens if two nodes accept conflicting writes for the same item? So this is where Dynamo makes an ingenious decision. So complexity of conflict resolution is pushed to read. So the system accepts the writes, but it is up to the what applications to deal with the messy versions later. So the question, see guys, the question then become who resolves conflict and read. So who resolves conflict on read? Guys, if the data store resolves it, okay, the only simple choice is last write wins based on the timestamp. So this is based on the timestamp. Okay. And the more flexible, powerful, but complex choice is to, what is that? Leave it to the application developer. Guys, Dynamo uses vector clock concept. Vector clock. What do you mean by vector clock? So which we will cover later. Okay. So vector clocks to let the what application decide how merge conflicting versions. See, for instance, merging two shopping carts instead of what just overwriting one. So finally, the system needs to scale easily. So it should incrementally add nodes and all nodes have systematic role like peers. So no single point of failure, guys. And because they use off-the-shelf machines. So it is a heterogeneous systems. So work is proportional to capability. Guys, faster nodes handle more work. A pragmatic and efficient design choice has been taken here. So these considerations always lead us to the specific architectural techniques used. Let's see them on the next slide. So look at here, guys. Architectural design we have mentioned here. So guys, this complete slide simply gives us the title, architectural techniques. So this is our roadmap for the next few slides. So we will explore the specific mechanism that Dynamo uses to achieve its amazing availability, durability, and eventual consistency. So let us break down this into complex topics like consistent hashing, okay, vector clocks, hinted handoffs, so Merkle trees, N bar, R bar, W quorum, everything. Okay, so let us start with the very first one. What is the first one? Guys, this consistent hashing is used for partitioning. And vector clocks for versioning and also conflict resolutions. So this is used for versioning and for conflict resolutions. And what about third one? Hinted handoff. So this is for repair and anti-entropy. And the next one, so NW bar, C N bar. Okay, Merkle trees. Next one is Merkle trees, right? So Merkle trees for, yeah, as I told, Merkle trees for repair and anti-entropy actually. So this hinted handoff is for fault tolerance, guys. This is for fault tolerance. And N bar, W bar, R quorum. Model for turning the trade-off between consistency, availability, and durability. These techniques are the backbone of any highly available distributed system. So buckle up, guys. So this is where the core engineering magic happens. So we'll start by looking at the technique related to what? Preventing data disorder. So which is the key for efficient repair on the next slide. Okay, object storage and interfaces. Guys, before we discuss about this, so I want you people to what? Concentrate on one more very important point. That point is Merkle trees. So let me explain you more about this anti-entropy. Let me write here. And Merkle trees. Let me discuss on these 2 points first. This is another very important one. Guys, the content of this complete slide a bit coincides, right? So we are focusing on reduce disorder and subtree roots keep track of differences of hashes in the children. So this is a fundamental concept for anti-entropy. So which is the process of detecting and repairing inconsistencies between replicas. So the mechanism describing here is that Merkle tree, or we can call it as hash tree. Okay, we will see this again on the next coming slide. But let's introduce the idea now. So let me take one analogy to explain on this, guys. You just imagine you have 2 identical books. Okay, or you can call it as 2 replica. So how do you quickly check if one page in one book is different from the same page in the other? So we are going to follow some algorithms, right? So let me start with the very first algorithm. So we are starting with brute force algorithm. So what is this brute force algorithm? Guys, read every word of both books. So which is very slow. And next we will jump to the second methodology that is called as Merkle tree concept. Guys, here the system divides the data into chunks. So we can call it as we can call the chunks as individual keys. It takes the hash of each chunk and then it groups two hashes and hashes that result and keeps building up the what tree until it has one single root hash. Now, to check for a difference, you just compare the two root hashes. If they are same, the replicas are identical. If they are different, then you can say you only have to what, compare the children of the root to quickly find the exact subtree. Thus, the small data chunk, so that is out of synchronization. So this allows the system to reduce disorder by only transferring the minimum required data to fix the inconsistency. Guys, it is an incredibly efficient way to check for data integrity and repair replicas on the background. So now we are touching upon the what? Next slide. So object storage and also interfaces. Guys, so let's get into the what simple but powerful interface that Dynamo and similar key value stores use. The fundamental principle is that objects are stored with associated keys. Objects are stored with associated keys. So it is a simple map, guys. Simple map. So that is key value. Key value. Okay. The interaction is defined by two main operations. What are that operations? This is the first operation. Object comma context is equal to get key. And second one, put key comma context comma object. So notice the parameter here, guys. What you have to notice here, the very first parameter context you have to notice. So this is a very important concept, guys. The context encodes system metadata along with version. Are you getting my point? So this context is used to encode the system metadata along with its versions. So it is not just the object itself, guys. The system wraps metadata around it. So this is how Dynamo manages multiple conflicting versions of the same object. Using that context, so which typically include vector clock, we discussed vector clock, we are going to discuss it later. Okay, so how is this data spread across cluster? Through partitioning and also replications. Guys, the variant of consistent hashing of the key is used to allocate storage nodes. So this is brilliant, friends. So instead of simple modulo hashing, so which breaks when a node is added or removed, consistent hashing minimizes the data movement. Okay, so we will explore this with the what? Code example later. Okay, so next point is each data item is replicated on a configurable member of nodes. So this number is n, guys. This number is n. Okay, so which we will talk about when we discuss n bar, r bar, w tuning. So replication is what ensure durability and also high availability. Now let us look at the what core mechanism for partitioning. That is consistent hashing using the what code example. I was telling you about code example, right? Now I'm giving you the code example. Look at the code example here. Okay, code DHT example. Look at the image given here. The image on this slide illustrates the code distributed hash table. So in short form, we are going to call it as DHT. So which is a classic implementation of consistent hashing. Guys, then what is the key idea here? The key idea is to arrange all the nodes and all possible keys on a logical ring. Okay. Guys, here we have what? The finger table, right? Look at here. This is the finger table I'm talking about. The finger table is the crucial piece of information stored on each node. Okay. So this points to where the object can be found or where the next pointer to the object is. So when you look for a key, okay, let me take the example as key is equal to K14. I'm talking about this K14, guys. Okay, when you look for this key, K14, you follow the ring. So data is stored on the first node whose ID is equal to or follow the key. Guys, in this example, if you look for what? K14, its successor, look at here, its successor, that is K14, successor K14 is N17, correct no? That is N17. Okay, so what is that N17? N17 is the node responsible for storing that key. Guys, consistent hashing solves the issue of adding or removing nodes by only affecting its immediate neighborhood on the ring. So most keys stay mapped to the same node. Most keys, look at here. I have taken arrow mark here. So, but how do you efficiently find the successor node in this ring? So we will look at what two ways. So one is we are going to use linear search. We are going to use linear search. So which is inefficient methodology. And the second one we are going to use logarithmic search. Logarithmic search. So that is using the what? Finger table. Okay. So now look at the what? Linear search example. Look at the linear search example here, everyone. So if we only use the simple ring structure of the chord DHT, the lookup process would be very slow. So that is illustrated in this example. Guys, look at here. I want each and everyone to look at here. See, lookup of X goes to the node. So this is your entry point to the system. Okay, lookup of X goes to the node. This is the entry point, guys. And the system would then keep following successor link of the nodes to check if object exists. That is the second point given here. So it is like a ring around the what? Rosy search, is it? Ring around the rosy search. The node checks if it is the successor. If not, it forwards the request to its immediate successor node. Then what is the problem, guys? The problem in a cluster with n nodes. So this is an big O of n message hops operation. If you just imagine, if you have 10,000 nodes, a single lookup could take 10,000 network hops. So that simply won't meet our latency requirement, guys. So however, a benefit of this basic setup is that the routing table in each node is big O of 1. So each node only needs to know its successor. So this is very simple for system maintenance, but awful for query performance. Guys, here we need a way to skip nodes in the search. So that exactly what the finger table provides. So let's look at the optimized approach on the next slide. See, this is the optimized approach. Okay. So all of them look at here. So this is where the chord DHT becomes incredibly efficient. So this is leveraging the finger table. Guys, instead of just knowing its immediate successor, okay, so each node stores a routing table which helps to search with big O of n log n, big O of n log n message hops. This is very important point, guys. So we have gone from linear time. So big O of n to big O of n to big O of log n. So if n is 10,000, then what is log of 10,000? So this is about 13 or 14 hops. You just calculate this. So 13 or 14 hops, right? So that's the massive difference in latency. Then you can ask me, guys, how does this work? Guys, the finger table has entries that point to nodes much further away in the ring. A node at n will have an entry for a node at n plus 2 to the power of k. Okay, let me write here. So n plus 2 to the power of k. So where k is the index here. So this is the index. Okay, so this, let's say what, requires to jump huge distances around the ring. So homing in on the what, target node very quickly. Guys, the trade-off is that the routing table itself now takes up more space. So space taken in routing table is big O of M. So big O of M. So where M is the number of bits in the address space. Okay, so 160 bit for what? Guys, you just look at the example. 160 bits required for SHA-1. Okay, so this is worthwhile memory investment for the performance gain. And the final consideration is the system stability. Okay, so when a node joins or leaves, the finger tables in some nodes need to be what, updated so that the change does not impact. The system has maintenance processes to ensure all these long distance pointers remains correct. Okay, to make this tangible, let's walk through small numerical example. So now all of them get ready with your pen and paper. So I'm going to solve numerical problems now. So are you all ready? So shall we take one numerical problem? Shall we take one numerical problem? So are you all ready with the pen and paper? Yes. Shall I get quick responses? Yes. Now look at here, guys. Let me take one small example to explain on this. So look at this example. I want each and everyone to concentrate now. Okay, let's ground the what concept of key mapping with a simple numerical example based on a small address space. Okay, guys, here the slide suggests, look at here, everyone. The slide suggests 7-bit addresses are 128 size key space. Guys, in this 7-bit system, the key space run from 0 to 2 to the power of 7 minus 1. What is the value, guys? 0 to 2 to the power of 7 means how much? 128 minus 1, that is 127. So totaling 128 possible positions on the ring. So 128 possible positions on the ring. Correct, no? The nodes are also assigning ID in this range. Here, the example shows, look at the example here. So 131 mod 128 we have taken. So that is indicating for what? 3. So that 3 is followed by N5. Okay. So imagine you have a key. Okay. Imagine you have a key. So let's call it as K. Let's call it as K. Okay. You hash K and the hash result in the number 131 hash results in the number 131. Since your address space only goes up to 127, you use modulo operator. That's why we have used modulo operator here. Okay. So why we are using modulo operator? Because we have to wrap the key around the ring. Correct, no? So we have taken 131 mod 128 here. So that will always give you 3 as an answer. So the meaning of this is the key is logically located at third position, position 3 on the ring. Position 3 on the ring. Okay, guys, the system then finds the successor node for position 3. So in this hypothetical example, N5, see in this hypothetical example, N5. Okay, N5 is the node responsible for storing the data at position 3. And possibly other keys until the what next node on the ring. Okay. And one more thing, guys, let me take one more. So N50. So let me take N50. So N50. Yeah, it is showing here, right? N50. So N50 showing here is the likely another node on the ring. So just to show the what distinction, that's it. So this simple calculation is the core of how consistent hashing works. So every node and every piece of a data is mapped to the ID on the ring. So which determines where it lives. So now we know how data is partitioned, also allocated, right? So let's talk about the complexity of highly available system. That highly available system is called as consistency. Consistency. Okay, consistency using versions. My dear friends, since we chose high availability over strict consistency, we need a way to deal with conflicts. Okay, the mechanism Dynamo uses for this is the vector clock. Vector clock. So make a note of this, guys. Vector clocks are critical in distributed system. Correct? No? I think everyone will agree with my point. A vector clock is not a single timestamp, but a set of what is a set of this, guys? So it is a set of node ID and also counter. It is a pair of two things. Guys, vector clocks are associated with every write. So that is the first point I have given here. Vector clocks are associated with every write. So when a replica receives a write, so it increments its own counter in the vector clock before storing it. Correct, no? So let me take one small example. Let me take V1. So V1 is equal to node A, comma, node A is to 1. Okay, node A is to 1. Key value pair I'm taking here. And next, node B, value I'm taking 0. So this is for V1. Okay, and what about V2, guys? What about V2? So V2, node A, this is node. Node A is to 1, comma, node B is to 1. Guys, here V1 is casually ordering before V2. So V1 can be overwritten by V2. So what about V3? So let me take V3 now. So V3 node A colon 2, comma, node B colon 0. Guys, here in this case, so V2 and V3 are concurrent and also conflict. Guys, the power, see here, the power is every read operations can understand the casual order and reconcile multiple versions. So when a client reads this V2 and V3, the vector clocks tells the client these two versions are concurrent. You decide how to merge them. So this puts the conflict resolution logic in the hands of the application. So that we have discussed, right? So in previous slide we have discussed, right? The same thing I'm explaining you now. Then what is the challenge here? Guys, we have a challenge here. The challenge is that vector clock can grow over time. This is a challenge. So here I have mentioned the challenge in the third point. If too many nodes participate in a write, the vector clock sizes increases. So that leading to what storage and performance over it. To mitigate this, Dynamo maintains a timestamp when last time a node updated a data item and deletes old nodes beyond the limit. So it is a pragmatic cleanup mechanism. So vector clocks handle data versioning. But what about node failure? Correct? No, we have to think about node failures also, right? So now let us look at how DynamoDB handles temporary fault. So that is showing in next slide actually. Guys, this mechanism is called as hinted handoffs. So this is one of my favorite concept in Dynamo design for fault tolerance, guys. Okay, this is one of the very good concept for fault tolerance. Okay, first let's define the core concept. What is the core concept we have to discuss now? The very first thing we have to discuss on sloppy quorum. Guys, listen to me carefully now. All reads and writes are performed by the first n healthy nodes. I think everyone will agree with my point. Correct, no? So first we will take the what? N healthy nodes and we will start performing read operation and also write operations perfectly. Okay, so and not n nodes in exact sequence, guys. So this is called as sloppy quorum. Okay, this is called as sloppy quorum. Guys, once I'm talking about normal quorum, a normal quorum is very strict here. The write must go to A first, then it has to go to B, then it has to go to C. Correct, no? But a sloppy quorum says the write needs to go to any three nodes. So this fundamentally improves what? Availability when nodes fail. Would you agree with my point, guys? This is the difference between these two. And let us discuss about inted handoff. Inted handoff now. Guys, inted handoff is the repair mechanism for the sloppy write. Okay, so let me take one small example. Look at here. So here we have taken one small example. Suppose node A was supposed to receive a replica along with B and C, but since A failed, it will go to D temporarily along with the int to D that A was the original choice. So before that, let me divide it into two parts, guys. So the first one, see, I'm taking from here. Suppose node A was supposed to receive a replica along with B and C, but A failed. That point I'm taking first. This is the very first point I'm showing you now. And after that, guys, the write will temporarily go to node D. The write will temporarily go to node D. Okay, so this node D is called as hinted node. Write down, everyone. So this is called as hinted node. So along with hint to D, that A was the original choice. Okay, so here we have mentioned A was the original choice. Guys, node D is now acting as a temporary caretaker. Correct, no? So this is behaving like a what? Temporary node taker. Once A is up, D will send replica to A, remove from itself. Okay, so the hint is handed off. Correct, no? So this is handed off. Now we are getting the meaning of hinted handoff. So this ensures writes are never lost due to a temporary node failure. Understanding my point, guys? See, for durability, the key hash based replica nodes are kept across data centers to be what? Highly durable. And also acknowledgement rights is kept more than one, so that at least two copies are written before acknowledgement to the client. So this is safety measure to confirm a minimum level of durability. Guys, what I would like to say here is inted handoff covers temporary failures. But what happens if a node is permanently lost? That is the challenge, right? Correct, no? This is the challenge we have to address here, right? Okay, so let me address this challenge now. What about permanent failure of nodes? Guys, if a node is permanently down, so we have a bigger problem. I think each and every one of you agree with this point. Then what do we, guys? We need a way to reliably detect inconsistency between replicas and solve it using minimum data transfer. So for instance, if node A is permanently gone, so if node A permanently gone, we need to quickly check its neighbor. So what are its neighbors, guys? Either I have to check B, or I have to check C, or I have to check D. Look at here. These are all neighbors. I have to check B, C, D. And make sure their replicas are fixed. Simple. Okay. So this is where we bring back the brilliant concept we introduced on previous slide, Merkle trees concept. So we have discussed about Merkle tree, right? Same thing I'm explaining you now. And Dynamo will use Merkle trees or hash tree to track down subtree where replicas have gone out of the synchronization. So as a reminder, the leaves are hashes of individual keys. A leaf hash represents a small chunk of data. Understanding? And the parents are hashes of children. Parents are hashes of children. So the permanent repair process, often called anti-entropy, works like this, guys. So how it will work? Let me show you step by step. The very first step is, first we will take node B and node C. Compare the root hash of their Merkle trees for the data range they share. This is the first step. If roots are different, they compare the children hashes. Okay, so they compare the children hashes. Okay, and they descend the what tree until they find the exact leaf hash that is different. So this pinpoints the exact key that is inconsistent, and only that key data needs to be what transferred to synchronize the replicas. So this is a powerful, elegant solutions for minimizing network traffic during background repair operations. Okay, so now that we understand replications, let's see how the number of replicas and the read or write confirmations can be tuned. See here, I was talking about NRW for performance, right? Look at here. So tweaking N, R, W for performance, durability, consistency, and availability. So my dear friends, this slide presents the famous NRW model for tuning consistency and availability in the distributed storage system. So this is a must-know concept for your exams and for your careers, guys. So this is must-know concept, guys. So I'm taking 3 stars here. This is must-know concept for each and everyone I'm telling you. Okay, so look at here one by one. So what is N here? Look at here, I've taken N. N is the number of replicas total for the data item. So here N is the number. I'm taking N from this number. The number of replicas total for a data item, typically 3 in DynamoDB. So by default in DynamoD, this is equals to 3. Then what is R? What is R? The minimum read replicas. So from R, see I've taken read R from the read. The minimum read replicas that must return data for the read operations to be considered successfully. And what about W? W means what? The minimum write replicas that must acknowledge the write for the write operations to be considered successful. Guys, by tweaking these numbers, so we can favor performance, durability, or consistency. Okay, see here, look at here, everyone. W is equal to 1. W is equal to 1. Only one node acknowledges the writes. So this gives you high performance writes as it's fast. But if that one node fails, the write is lost. That you should remember. Okay. So next we are taking W is equal to N. So next we are taking W is equal to N. What is N? N is nothing but all, right? All replicas must acknowledge the write here. So this gives you high durable writes. High durable writes. So it is slow, but the write is guaranteed to be on every node. And next we have taken R is equal to 1. So only one node needs to respond to the read. So this gives you high performance read. It is faster, but you might read stale data. And finally, R is equal to N, right? So all replicas must respond and agree. So this gives you highly consistent reads. So it is low and it could fail if one node is down. So hope everyone understood this. And consistency, guys, consistency C is achieved when R plus W is greater than N. Okay, so let me take one typical configuration in DynamoDB. Okay, so that is N comma R comma W equals to 3 comma 2 comma 2. See here in this case, 2 plus 2 is always greater than 3, right? So you have quorum based write and quorum based read. So which means a read will always overlap with the latest successful write and giving you strong consistency in the theory. Okay, the final point reminds us that even with this model, it is a hard engineering problem. See here I mentioned, the last point I mentioned here. Hard engineering problem to use commodity heterogeneous hardware and provide 99.9th percentile SLA on latency. Guys, accommodating the slowest replica for R and W targets is the real challenge. Okay, now let us switch our gear from Dynamo paper to the DynamoDB service. Okay, so here, so we are more talking about DynamoDB service. So guys, we are now diving into AWS DynamoDB. Let me see if any questions are there in chat box. So till here, everything is clear, guys. Shall I get quick confirmation? I'm not getting any messages on chat box. Is this clear? Till here, everything is clear. Okay. Okay, guys. Guys, it is a NoSQL store that can store nested JSON documents in table. So this is the table. So we have placed JSON documents inside this. So this is fantastic, friends. DynamoDB is not just for a simple key value pair. It is a document database where the data, where the what value can be complex JSON structure up to 32 levels of nesting. Up to 32 levels of nesting. So this provides great flexibility for modern application data. Okay, guys, here the way we query and partitions data is through what keys? See here, I have mentioned second point. Partition keys using consistent hashing. So this is our old friend, right? So consistent hashing, this is our old friend, right? So which determines which node the data lives on. The partition key is often called hash key here. This is often called hash key, or we can call it as primary key. Okay, in a single key table. So its value is hash to spread the data evenly across the cluster. And look at the next point, optional sorting key to sort within a partition. So if you have a partition key, okay, let me take partition key as user ID. And sort key, you have a separate sort key. Let me take sort key as a timestamp. So this is partition key and this is your sort key. See, all the items for user ID are stored together and sorted by this timestamp. So this allows for highly efficient range queries like get all order for this user between date X and date Y miss. So easily I can get the data back. Okay, so this dual key structure is a very important concept for designing high performance DynamoDB tables. But what if you need to query by an attribute that is not one of these two keys? That's what we call secondary index. So that secondary index I'm explaining you in the next slide. Look at here. Secondary indices. I'm talking about secondary indices now. My dear friends, the ability to query data effectively often requires looking up items based on the different attributes. So this is where secondary indices come into play in DynamoDB concept. Okay, so there are two main types, guys. The very first type is called as global secondary indices, and another one is local secondary indices. So this is in short form, we are going to call it as GSI, and this is LSI. Okay, guys, let me start with the very first one, global secondary indices. Guys, this index has its own different partition key and own sort key. So entirely separate from the main table keys. So let me take one analogy to explain on this, guys. So think of the main table as a book indexed by title. Okay, a GSI is a separate full text index for the same book, but indexed by author. Okay, so it allows for queries that are completely separate from the original key. Okay, so here we are using the term global, right? So why we are using the term global? Global means it spans all partitions of the original table and essentially creates a new distributed table. Okay, so next we have LSI, local secondary index. Guys, this index must have same partition key but different sort key. So what is the analogy? Yes, think of our main table being indexed by user ID and also timestamp. And LSI would be what? Indexed by user ID and order status. So user ID is same here. So same partition key I'm using here, but different sort key I'm using here. So in my example, it is timestamp. But here what I'm taking order status. The data is co-located in the same partition, but the secondary index allows you to query it based on the different sorted attribute. Guys, then what is the meaning of local? Why we have used the keyword local? Local means the index is scoped to the partitions of the main table. Guys, what we have to understand at the end, the presence of a global secondary index is a powerful feature that gives DynamoDB much of its flexibility. But remember, GSIs are eventually consistent by default. So this is eventually consistent. Okay. So which brings us to our next topic, consistency. So let me talk about consistency here. Guys, after incredibly useful feature that extends DynamoDB beyond just a data stores is called as streams. Okay, a DynamoDB stream is essentially a change log for your table. So it captures data modification event if enables on the table. So think of it like this, guys. Every time you change a record in your table, that action, the event is logged in the stream. Okay, on new item, update, delete the item, timestamp, table name, metadata creates a stream record. So this provides a chronological ordered sequence of every single change. Then you can ask me a question, sir, why is this useful? So this is useful because you can attach triggers can be created by adding a lambda function. Okay, so example for this is, see, this is the example we have taken here. So look at the example. So this is the great example given. Okay, send welcome email to new customers. Send welcome email to new customers. This is the best example we have taken for this concept. So when a new customer record is inserted into your customer table, the DynamoDB streams capture that event, triggers a lambda function. Okay, it will trigger a lambda function. Okay, that lambda executes the code to send the welcome email. Okay, so this is the power of reactive architecture, guys, where database changes automatically kick off application logic. Okay, it is a fundamental pattern in modern serverless computing. Now let us talk more formally about the consistency model available in the DynamoDB. So DynamoDB consistency we are talking about here. My dear students, so this is another very important slide. See, understanding DynamoDB consistency option is crucial for application development. So recall that DynamoDB tables are highly available. A table may be in multiple regions and replicated within the region at AZs. By default, DynamoDB uses eventually consistency reads. So here we have mentioned few advantages. The advantages of this is faster reads. So this is the highest performance options, guys. But along with this, we have some disadvantages also. What are the disadvantages? This is the disadvantages. Stale data may be returned. Stale data may be returned. You might read a version of the data that does not include a recent write. Guys, in practice, it is typically consistent within 1 second. Okay, so if your application must see absolute latest data, you can request a strong consistency. Understanding my point? You do this by setting consistent read is equal to true. So this is you have to set actually. So this you have to set during the what? Query. Then what are the advantage of this, guys? The advantage of this is, see, the very first point is given as an advantage. Return latest write for the reads. So you are guaranteed to see the most up-to-date data. But we have a disadvantage with respect to this also. Disadvantages are highly latency reads. This is the disadvantage. Highly latency reads, and reads may be unavailable on outage. Reads may be unavailable on outages. So as the system cannot sacrifice the C for A in the cap theorem. And global secondary indices are not supported for reads. This is very, very important point. So you can only query the main tables key, and it uses more throughput capacity for reads. So making it what? More expensive. So the rule of thumb is use eventual consistency unless you absolutely cannot. Understanding my point, guys? So next up, we will see how AWS charges you for all this power. That is called as the capacity model. So here we have a capacity model. Guys, the billing for DynamoDB is directly tied to the concept of capacity model. It depends on the capacity model, which you set on a table. Guys, you have two options here. The very first option is called as provisioned, that is by default, and second one is on demand. So let me go with the provisioned one first. You reserve this is default, guys. You reserve capacity for read or write throughput needed. So you tell AWS, what you have to tell? I need 1000 reads and 500 writes per second. That's all. Very simple. Okay. The advantage of this is cost predictability. You know your bill upfront, right? And it can still auto scale between levels, but within the bounds you define. So that is provision. Then what about the on demand? Guys, on demand means this is a pay as you go model. So this is a pay as you go model. Okay. Pay as you go model. Correct, no? It needs no capacity planning. So it is good for unpredictable workloads that need fast response and pay for use. So it offers single digit MS responses on the read or write. Understanding my point, guys? So important detail. What is the important detail here, guys? Auto scaling happens within time limit. See, for example, it might scale if the workload doubles after 30 minutes. But it will throttle requests that spike too quickly. And here guys, the final piece of understanding the unit is capacity units. Okay, what is this capacity units? See, read request unit is equal to 1. So read request unit is equal to 1 unit we have mentioned here. So one strong consistent read of an item up to 4 KB, in size, or two eventually consistent reads of item up to 4 KB. Okay, so this is a great reminder that eventually consistent reads are of the cost. And next one, I have taken write request unit is equal to 1 unit. So 1 cross 1 KB write or 0.5 into transactional 1 KB write. See, transaction cost doubles the capacity. So this is a key area of optimizing for any big data systems on AWS. Okay, now let us look at how we actually interact with the data in a DynamoDB. So that is called as CRUD operations. So guys, let's see the what practical sides of interacting with DynamoDB. So it is covering create operation, read operation, update operation, and delete operations. So consolidating, we are going to call it as CRUD operations. So you have two main options. Okay, what are the two main options? The very first option is called as partitional query language. It is okay. This is a what SQL compatible query language for the DynamoDB, and it is much easier for those with relational background. And second one, APIs. So you can use direct programmatic call. So for example, you can take put item, get item, update item, So this is typically using JSON syntax. Understanding my point, guys? And guys, you can look at here. So this complete slide is giving excellent example. Let's look at few, guys. So the very first one is table definition. Guys, the JSON shows the table music. I'm starting from here. Table name is music. It defines the key schema. So inside key schema, you just look at here. Artist as the hash key. This is the hash key we are using here. So this is the hash key we are using here. And what about the next one? See, next one is song title, right? So song title is sort key. Actually, this is the sort key we are using here. So it also specifies provisioned throughput. So what is the provisional throughput it is providing? One read and one write unit. One read unit and also one write unit. Understanding, guys? So this is about the first table. Next one is insert with partition query language. Guys, look at the statement here. Insert into music. And then we have taken some values here. So inside bracket, inside simple brace, and then we have taken values. And inside that we have taken some values. Correct, no? So this is straightforward SQL syntax. Okay, what you have to notice here. See, notice the tags attribute is the complex. See, tags attributes are the, see here we have used tags attribute, right? Correct, no? So tags attribute is a complex JSON string. So this shows its ability to store nested data. Understanding? And next to that, we have a selector. See, look at here. Third one is select with partition query. So select a star from music where artist is equal to something, something, something we have mentioned here. So guys, partitional query language allows for powerful filtering after the initial key based lookup. So all of them, make a note of this, guys. So DynamoDB must use hash key. What hash key it is using here? Artist hash key it is using here for the what? Initial lookup. And then can filter the what results using like option. Look at here. We have taken like and also we have taken less than symbol. By using like and less than causes, it will filter the results. Understanding my point? And the second methodology also we have taken here. This is API query actually. API query. Or we can call it as key condition expression. So this is old school API way, guys. You define the exact query using key conditional expression and bind the values using expression attribute values. See here, we have used key condition expression and expression attribute values also we have used. So this is often faster for applications, but harder to write manually. My suggestion is you always go with the very first one. So partition query language. So this concludes our deep dive into the DynamoDB architecture. So Dynamo architecture and also the DynamoDB services. You now have a solid understanding of high scale NoSQL key value store. Okay. So now we are transitioning from DynamoDB to the next major topic, that is Apache Spark. I will assume. So each and every one of you what understood this. So you have to go with the practical thing, guys. Then you will understand everything clearly. Okay. So guys, now we are ready to what move from the word of distributed storage to the word of distributed computations. Okay. So storage to computations. So we are beginning our journey into Apache Spark. The unified engine for what is Apache Spark, guys? That is one of the what unified engine for large scale data processing. So this is an incredibly exciting and highly sought after skill. So let's give it our what full attention. Okay. So can we do one thing? So before we are moving into this concept, so can we take a 10 minutes break? Can we go for 10 minutes break? Yes or no, guys? Now the time is 7:10. So we can take break till 7:20. Okay. So after that, I'm going to extend the class for 10 minutes, guys. Thank you, guys. We'll come back at 7:50. 7:20. Narayanan, you discuss with Kamlesh sir. Okay, you send a mail to him, so he will resolve your problem. Okay. Guys, actually, we have LF, right? Leading learning facilitator. Suppose you have any problem, means you just discuss with Kamlesh. Okay, you send a mail to him. So he is resolving many problems. That's why, guys, initially we asked you people to come out with your own teammates. But that you people have not done. So because of that only all these confusions. Okay, you discuss with Kamlesh, so we will definitely give you the solution. Is this clear, Narayanan, Rajkumar? Yes, I'm not getting any responses from Narayanan and also Ravi Kumar. Okay, you people send a request to him, so he will resolve your problem. I think Rajkumar, for you, he has solved your problem, right? Why again confusion? Okay, this we can address at the end, guys. So let me complete the portion first. Yeah. Guys, yes. So now we are diving deeper into the computational part. So this is topics for 13th session. So this is the second major part of our session today and is the introduction to Spark. And we'll be focusing on 4 key areas here. So the very first one is introduction. Okay. So, and then we are getting, see, introduction means we will understand what Spark is and why it is so revolutionary. That is the first point we have to discuss. And getting started. Next one is getting started. Guys, we will look at its language support and also its relationship with Hadoop. And next to that, we have a setup, a quick walkthrough of how you get the software and run it. And finally, we will take some sample examples. So we look at fundamental data structure. So that is RDD concept and how you interact with it. So all these concepts we are discussing in today's session, guys. To understand Spark's necessity, so let's quickly remind ourselves of the landscape of big data computing engines that existed before Spark came along. Okay, so look at the very first slide here, guys. So before Spark, the big data world was fragmented. Correct, no? Yes or no, guys? Each type of data problems require a different specialized tool. Okay, for batch processing, we need Hadoop. See, the batch processing was dominated by Hadoop MapReduce. And stream processing, handling real-time data from sensors or logs, was managed by the engine like Storm. And for interactive processing, where analysts needed fast SQL queries on massive data sets. So new tool like Thais, Impala emerged. And for graph processing, see what we did in graph processing, analyzing relationships like social networks. You had a specialized system like Neo4j. Okay, through primarily a graph DB. So it has a strong graph processing capabilities. Guys, the problem was complexity and also overhead here. Correct, no? So if you wanted a single data pipeline that did an ETL batch job, so then ran a machine learning interactive algorithm and finally fed the result to a streaming dashboard. You had to glue 3 different systems together. So this fragmentation is what Spark set out to solve. So which leads us to the core questions on the next slide. Okay, so look at the question given here. So is it to create a general purpose computing engine for big data analyst? So this question we have to answer. The simple answer is yes. The simple answer is yes here. So, and we are going to use the engine Spark. Okay, guys, Spark is defined as a cluster computing platform. Here we have given the definition. It is defined as a cluster computing platform. So it was designed to be fast and general purpose. So let's break down these two pillars. So let me talk the very first one as a speed and second one is generality. I'm taking both the points here. So speed is crucial. We all know that. So as it creates a difference when data is being explored. Guys, faster processing means faster iteration for data scientist. Okay, it extends MapReduce model, building upon that idea, but making it much more efficient. Okay, guys, the secret sauce, it runs computations in memory. This is the secret sauce. So this is the single biggest performance differentiator from Hadoop MapReduce, which writes intermediate result to the disk. So this is about fast, guys. Then what about generality? Guys, Spark covers a wide variety of workloads which earlier required different distributed systems. So this is its unification power. So this is the unification power. Okay. So it includes batch applications, means iterative algorithms, so interactive queries, streaming. So it makes it easy and inexpensive to combine different processing types in the data pipelines. Guys, Spark is a Swiss Army knife of big data. Remember this. So it eliminates the need for multiple complex systems in your pipeline. Okay, so let us look at the what accessibility on the next slide. See, this is the accessibility. Guys, the widespread adoptions of Spark is due not only to its power, but also to its accessibility. Guys, Spark handles highly accessible, simple API in multiple languages. So making it a friendly environment for different developers. So Java, Python, Scala, and SQL. Since Spark is written in Scala, so this complete Spark is written in Scala, guys. Try to remember this. Since Spark is written in Scala, Scala is often the most performant choice. But guys, you all heard about PySpark, right? You all heard about PySpark, right? So PySpark, it is the Python API, is usually popular with the data science community. And even SQL support is a game changer for the data analyst. Guys, crucially, Spark integrates easily with other big data tools or platform. That is the big advantage of using Spark. It works seamlessly with the Hadoop ecosystem and especially HDFS file system. And it can ingest data from the streaming platform like Kafka. And of course, guys, it runs effortlessly on major cloud platform like AWS. Guys, this integration point is very key point, guys. It shows this Spark is designed to augment, not replace existing infrastructure. Since we mentioned Hadoop, let's spend a moment on the relationship between Spark and its predecessors. So that is nothing but your Hadoop. See, I'm spending one slide to explain the relationship between Hadoop and also Spark. Guys, the history is clear, right? Spark was introduced to address the speed up of Hadoop computation. So Hadoop MapReduce was the foundation, but it had glaring performance issues. So make a note of this, guys. This point is very, very important. So all of them make a note of this. Okay, Spark is not modified. Spark is not modified version of Hadoop, but it can use Hadoop as an option. So it is its own independent engine, guys. However, it can use Hadoop as a helper. Okay, so it can use Yarn, yet another resource negotiator for cluster management, and it can use HDFS storage. Guys, the distinction is that Spark has its own in-memory cluster. In-memory cluster computations engine using RDD. So RDD is nothing but resilient distributed data sets. Okay, so this is what gives it the massive performance boost, guys. And finally, while Hadoop was limited mostly to MapReduce, Spark support more than MapReduce. Okay, so it is including native libraries for SQL, native libraries for streaming, machine learning, and graphs. So why did we need Spark? Let's detail the what? Inefficiencies of MapReduce that it addressed. See, here I'm showing you the inefficiency of MapReduce. Guys, MapReduce was a breakthrough. So yes, we have to agree with that. But it was designed around the idea of reliably running jobs on unreliable commodity hardware by writing everything to the disk. So this is where its inefficiencies shows up, and especially for interactive applications. Okay, especially for iterative applications, not interactive, guys, iterative applications. Guys, iterative algorithms like, so those used in machine learning. So let's talk about K-means algorithm that need to what? Repeat the same set of computations over the same data set multiple times, right? With MapReduce, this incurs significant overhead at the end of every iteration. Okay, so let me take the very first one, serialization. See, data must be converted from Java object to bytes and alls, bytes and back. And second one is disk input output. The intermediate output of one MapReduce job must be written to disk. And third one is replications. Since HDFS is fault tolerance, so this intermediate data is also replicated across the cluster. So these three steps for every iteration lead to massive slowdowns for machine learning and also graph algorithms. Okay, the second major inefficiency was in interactive analysis, so which we will see in the next coming slide. Interactive operations. Look at here, everyone. The second significant inefficiency was with interactive operations. Okay, I have written here interactive operations. So which are essential for exploratory data analysis, EDA. Guys, interactive queries require a rapid feedback loop, correct? No? But with MapReduce, each query is a separate job that needs to read its input data. So which often means reading from stable storage like your HDFS. Guys, in this scenario, so the disk input output here I have mentioned, disk input output will dominate application execution time. So the user is waiting minutes for a query that should take seconds. Okay, let me give you an analogy to understand this, guys. So think of it like a what chef. So chef is your MapReduce. So who has to clean all the pots and pans, put them away, and then retrieve them again for every single step of the three-step recipe. So it is reliable, but incredibly slow. Then what is the Spark solution? Guys, Spark solution is to both of these problems is simply yet profound. So we are using in-memory concept. Okay, we are using in-memory concept here. In-memory computing, we can call it as in-memory computing. Look at here, guys. I'm talking about in-memory computing now. Guys, this is the secret weapon of your Spark. In-memory computing using RDD, resilient distributed data set. So I want each and everyone to remember this. So the first critical point is to store intermediate result in distributed memory without complications user programming. What is the meaning of this, guys? So this is the direct antidote to the disk input output problem in MapReduce. Guys, once the data is loaded for the first computations, the result of the intermediate steps are kept right there in the cluster's RAM. So ready for the next step. For iterative algorithms, so this cuts the time from minutes to the seconds. Correct, no? But what if data sets is too big for a cluster's total memory? Correct, no? Guys, here Spark handles this gracefully. So spillover can be transparent stored on disk. The system will use memory first, and if it runs out, it automatically spills the excess data to the local disk. Okay, so this is a make a note of, see, this is a very, very important point, guys. So that's why I want you people to make a note of this. The performance gain is massive here, but it introduces a new constraint. What is the new constraint it is introducing? Spark performance is highly dependent on having enough RAM. So this is always depends on the capacity of your RAM. Okay, so now let's quickly confirm this on the next slide. So which reinforces the what? Same brilliant idea. Look at here, everyone. Guys, this slide repeats the what? Key concept, emphasizing the importance of store intermediate results in distributed memory without complicating user programming. And that spills over can be transparently stored on disk. So I want to reinforce the idea of without complicating user programming. So without complicating user programming. So in order, see, in older systems, the developer had to manually manage caching and writing to disk. Okay, so Spark's RDD is the abstraction that manages this memory and disk utilizes transparently for you. Guys, you as a developer just write a few lines of code and Spark's runtime engine optimizes the memory use. Okay, so this powerful abstraction is what we need to define formally. So let's answer the question, guys. What exactly is the RDD? So I'm telling you about what RDD, right? Then what do you mean by RDD? So now I'm giving you what the definition of RDD here. Okay, this is the most fundamental concept in Spark, guys. So focus up, each and everyone. RDD is nothing but resilient distributed data set. So this is the cornerstone of your Spark concept. Guys, look at here. It is a fundamental data structure in Spark. So it is the primary way you interact with the data in the original Spark Core API. And one more point. So it is immutable distributed collections of objects. You know what is immutable, right? What do you mean by immutable? Can anyone answer? What do you mean by immutable? What do you mean by immutable, guys? Once created, you cannot change it. Correct? No? That is called as immutable. See, any transformation, see, like map or filter, creates a new IDD here. So this is the key for fault tolerance. Correct? No? Key for fault tolerance. And the second point we have mentioned here is distributed. See, immutable, we have understood why it is distributed. The collection is spread across the cluster worker nodes. Then how do we create this, guys? How do we create this one? So you can create one from an existing local collections by calling this methodology, that is parallelize. Okay, this is an existing collections in the what driver program. So let me what take with the example here. Data is equal to, we have mentioned 1, 2, 3, 4, 5. Then we have written distinct data is equal to sc dot parallelize. See, parallelize, this is Z, guys. Parallelize, so we are passing data. So this pushes your local list out to the cluster. So more commonly, you reference a data set in an external storage, that is HDFS or HBase. So this just creates a pointer to the data without loading it. So it is allowing you to operate on it, guys. That's all. So let's break down the what? 3 words in RDD name. What are the 3 words we have used here? So we have used resilient distributed data set, right? So what do you mean by this, guys? The name resilient distributed data set is an absolute masterpiece of naming. So as it captures the what? 3 core properties of this abstraction. So the very first one, resilient. So this refers to its ability to recover from fault. Try to understand this. See, here we have given a definition. A lineage graph of operations helps to reconstruct when a node fails and part of an RDD is lost. Same thing, no? So let me take one analogy to explain on this, guys. So think of it like a recipe. Okay. The RDD does not store the final cake. Understanding my point? The RDD does not store the final cake. It stores the recipe. That's all. So that recipe is called as, what is recipe here? Recipe is nothing but transformation. Recipe is nothing but transformation here. Okay. If the cake is lost, so Spark simply follows the recipe again from the original ingredients to quickly rebake the missing piece. So this is a vast improvement over manual checkpointing in older systems, guys. So is it not interesting? Is it not interesting, guys? So I think by using this analogy, you have understood, right? What do you mean by resilient? And the next keyword is distributed. So this is straightforward, guys. So each RDD is divided into logical partitions for parallel computations on a cluster. So this is how we get horizontal scalability. So this is, we are talking about horizontal scalability. And what is the last one? Data set. So this is simply means set. So it can contain any type of object depending on the language used. Guys, it could be a collection of integers in Scala or Python objects or custom Java classes, guys. Anything. So that is comes under dataset. So this inherent resilience through lineage is what makes RDD so powerful. Okay. On the next slide, we will discuss when to use RDD versus the newer Spark API. Look at here. So options in Spark API. Guys, when should you choose the raw RDD API versus the more modern data frame or dataset API? Guys, the answer is the RDD API is your low level choice. Understand this. So this is a low level choice. So it is useful. It is useful when dealing with unstructured data. This is very, very important point, guys. Unstructured data like raw text logs, binary files. And when you don't want to impose a scheme, okay, when you don't want to impose a scheme, and when you need low level operations on the data. So these are not interested in optimization done for structured data. So however, the slides point out the advantages of the newer APIs. So which use concepts like named column. Named columns are the fastest option, correct? No? And have added type safety. So these are the features of data frames and also data sets, guys. So which we will cover in the later session. So they work with the structured data and allow Spark's internal optimizer to create a much more efficient execution plan. Okay, so now let's stick on to the what? Core features of the RDD itself. So here I'm giving some core features. Look at here, everyone. So the very first one is, let's synthesize the what main operation features of the RDD. So what is the very first point? Keep data in memory as much as possible. Guys, this is the core performance mantra. Correct, no? In Spark, this is the mantra always we are going to use, guys. And what is the second one? evaluate only when an action triggers. So this is called lazy evaluation. So everyone note on this. So this is called as lazy evaluations. Guys, an RDD transformation. Okay, RDD transformation does not run until an action is called. So I will tell you what is transformation, what is action later. But for a time being, you just means go through this what explanation, guys. An RDD transformation. Transformation is nothing but a map, right? And action is nothing but what operations we are performing, whether we are performing count operation or collect operation, whatever it is. The transformation always does not run until action is called. So this allows Spark to build up the what recipe and optimize the entire computation graph before executing. Okay, and look at the third point. A failed lost RDD partitions on a worker can be recovered from lineage of operations. So this is its resilience again. And it cannot change once created. Already I've told you about this, right? What we are going to call it as immutability. Immutability is the foundation of recovery. And next point is persist in memory or storage for use. See, if you have RDD used in multiple iteration, you can explicitly cache it to keep it in RAM. Okay, and parallelism through partition. Next feature is parallelism through partition. Guys, here in this case, data is broken into chunks for parallel processing. And put task closer to the data location. What is the meaning of this, guys? Guys, always see, this is very, very important. Spark tries to achieve data locality. The meaning of this is we are moving the computations to the data, not the data to the computation. I hope everyone understood this point. And finally, apply operations entire set of data at coarse grain and not data item within the RDD. Guys, operations applied to the whole partition, whole data set, guys. So which is more efficient than fine grained item by item updates. Guys, these features make RDD what they are. But they are not without their problems, guys. Correct, no? So now look at the limitations of RDD. So here we have listed few limitations of RDD. While RDDs are groundbreaking, so they have limitations. So which is why Spark introduced data frames and also data sets actually. What is the first problem, guys? Optimizer problem. For structured data, RDD do not exploit any optimizers. Okay, this is for the structured data. So if your data is tabular, okay, so the meaning of this is if your data is database table, the RDD API does not allow Spark to reorder joins or simplify the filters. So this is why it is better to use data frame or data sets. So which can use Spark Catalyst Optimizer. Okay, and what is the second one? The second limitation is overhead, guys. So this is the overhead. Guys, since RDD are in-memory JVM object, so there are garbage collections and Java serialization overhead. What is the meaning of this, guys? Guys, every time objects are created and discarded, correct, no? Then what Java virtual machine will do, guys? Java virtual machine has to run its garbage collector. So which can pass the application and hurt the performance. And third one is memory constraint. See, this is explaining about memory constraint. The fundamental limitation is still memory, guys. Correct, no? See, spillover data is put on disk, which slows down the performance. Hence, machines needs to have enough memory, gives the data size and also analysis. Okay, guys, if you have to spill too much to disk, you are back to the what MapReduce problem. Am I right or wrong, guys? So these are the what limitations of your RDD concept. Let's use a what comparative tool to understand RDD even better by comparing them to another in-memory architecture, that is distributed shared memory. So that is this concept, guys. So how many slides we have completed? I will do one thing, guys. So let me complete. So we have left with so many slides. Shall I continue till 49 slides, guys? Shall I continue till 49 slides? So now we are at 41st slide. Okay, 39 slide. So we are at 39 slides. Shall I complete 10 more slides? Yes or no, guys? Shall I take 20 more minutes? Otherwise, it will become burden for me to complete the syllabus, guys. Shall I proceed for 20 more minutes? I'm not getting any responses. What happened to you all, guys? Yes, okay. So I will continue till 49th slide, guys. Now I am at 39th slide. Let me complete at least 10 slides. So remaining 10 slides I can complete in the next coming class. Okay. Okay, fine, guys. Look at here, everyone. Thank you. Thank you for your cooperation. So everyone look at here. So I was talking about RDD and distributed shared memory, right? Guys, RDD concept is often compared to distributed shared memory systems. So let's look at the what key differences. So here I've taken features. So the very first feature what I've taken here, gain of read or write operation. Guys, with respect to RDD, we have taken here. See, RDD is coarse grained. See, here we have mentioned coarse grained. The meaning of this is, so works at the entire data set level. That is the meaning of coarse level, coarse grained actually. Whereas in case of what DSM, so it is fine grained. Let me write here. It is fine grained. The meaning of this is, so works at the specific data item level. That is one difference. And what is the next one? With respect to consistency, the next keyword I'm taking here, consistency. See, already we have discussed about this, right? Immutable RDD are trivially consistent. So since they cannot change, there is no consistency problem here. Am I right or wrong, guys? But what about distributed shared memory? Distributed shared memory makes. See, this requires complex mechanism to make sure of consistency if the programmer follow a set of rules. And the third key point is fault recovery. So fault recovery. Guys, recovered by following lineage of operations. The recipe is rerun. So in the case of what? Fault recovery. But in DSM, so DSM is need checkpointing rollback. So this is manually managed, state heavy and also expensive concept. And the next keyword I'm taking, straggler mitigations. Guys, in RDD, RDDs make it easier with backup task. If one task is slow, a backup task can be launched on another node. That is the advantage of using this with respect to what? DSM I'm telling you. So in case of DSM, it is very difficult, guys. So it is difficult in case of DSM. And the last key point I'm taking here is out of memory behavior. Guys, with respect to RDD, data spills over, goes to on-disk RDD. So gradually degrading performance. But in case of DSM, system swaps may lead to what? System instability. That is one of the what differences. See, these are the differences between these two, guys. See, what is the key takeaway here? Guys, RDD always prioritize reliability and fault recovery through immutability and also lineage. So making them what? A much more robust abstractions for big data applications. So this RDD abstraction is the foundation for the entire Spark ecosystem. So which we will explore now. See, look at the diagram. So this is showing unified stack reference. Guys, this slide so completely introduces the concept of Spark unified stack. So it is a reference to the architecture that takes the core RDD concept and built specialized tool on top of it, guys. See, at the bottom of the stack, what do we have at the bottom of the stack, guys? So we have Spark Core. Okay, we have Spark Core. So make a note of this, guys. Core is the base layer. So this is the base layer here. Okay, so it contains the basic functionalities of Spark. So it is including the components for task scheduling, memory management, fault recovery, and interacting with storage systems. So this is the brain of Spark, guys. Try to remember. Okay, so it is the home to the API that defines the resilient distributed data set. So which are Spark's main programming abstraction. Okay, so it provides many APIs, guys. It provides many APIs for building and manipulating these collections. Okay, so everything else in the Spark ecosystem is built on top of the core. So this modularity is why Spark is so general purpose and also extensible. Now look at the first major library built on core. What is that library, guys? That is Spark SQL. See, these all points I have explained you, right? See, the diagram related points already I have explained you. So now I'm talking more on Spark SQL. Look at here, everyone. Spark SQL. This is very, very important one, guys. Okay, so Spark SQL is the layer that enables you to work with structured data efficiently. Okay, this is for structured data, guys. So it is Spark's package for working with structured data. Remember this. So the meaning of this is data that has a schema, column names, data types like table. So this is where data frames and data sets lives. And it allows querying data via SQL as well as Apache Hive variant of SQL. Okay. So for the vast community of data analysts who know SQL, this is a huge. Okay. So it has the ability to intermix SQL queries with the programmatic data manipulation supported by the RDDs. So you can use Python language, you can use Java, Scala. So all within the single applications. So this is the unification power in action, guys. You can run a SQL query, take a result, and then run a Python machine learning algorithm on it. So all in one seamless Spark job. The tight interaction makes Spark SQL a much more powerful platform than traditional open source data warehouse tools. Correct? No? The Spark SQL handles static structured data. But what about the data that never stops flowing? That is called as streaming, right? We are going to call it as Spark streaming. Now we look at the component that allows Sparks to handle real-time data. That is called as Spark streaming. Okay, guys, this is the Spark component that enables the processing of live stream of data. So example of data stream include web server log files that are being generated constantly. And it provides an API for manipulating data streams that closely matches the Spark Core RDD API. It uses a technique called dstream concept. Okay, it uses the technique called dstream. Remember this. Dstreams. Dstreams are nothing but discretized streams. So which essentially breaks the continuous streams into teeny ordered batches of the RDD. Crucially, guys, so it is designed to provide same degree of fault tolerance, throughput, scalability as a Spark core. The meaning of this is the recovery and resilience features of RDD are brought to real-time data. Guys, Spark streaming is your go-to for low latency dashboard and real-time anomaly detections. Correct? No? Now let us look at the library that made Sparks a favorite for data scientists. What are those library? Yes, that library is called as MLlib. My dear friends, this is very, very important one, right? This is very, very important one, right? MLlib. So it is a built-in library containing common machine learning functionality. You don't need to import external frameworks, guys. So it provides a wide range of ML algorithms. So including classification, regression, clustering, collaborative filtering, supporting functionality. Okay, see, whatever your core ML task, MLlib probably has a scalable implementation. Okay, here I mentioned, right, the last point. So that means it also includes the what supporting functionalities like data import and also model evaluation. The key is that all of these methods are designed to scale out across the cluster. So when you train a model, Spark automatically distributes the computations across all your worker nodes, allowing you to train models on massive terabyte scale data sets that would crash a single machine. So this is what fully unified the platform. You can load data with Spark SQL, clean it with Spark Core, and train a model with MLlib. So all in one place, guys. Is it not interesting? It is very much interesting, right? So now let us look at our final major library. What is the final major library? That is GraphX. Maybe you have heard about GraphX. Guys, GraphX is the specialized library for graph parallel computation. Okay, guys, it is a library for manipulating graphs. See, example, social network relationship graph I've mentioned here. So think of a social network users. So social worker, social network users are called as vertices here. And the relationships are called as edges. Guys, it extends the Spark RDD API. So allowing us to create directed graph with arbitrary properties attached to each vertex and edge. And it provides libraries of common graph algorithms such as PageRank. So it provides PageRank, guys. Okay. See, you know, right, that PageRank is used by Google to rank the web pages. And also we have a triangle counting. So that is used to measure social cohesiveness of the network. Guys, GraphX completes the Spark generality portfolio. So that is covering batch, iterative, interactive, streaming, SQL, now the graph problems. Guys, a brief but critical look at how Spark is deployed. Cluster management. Okay, my dear students, a powerful engine like Spark needs a what? Powerful deployment environment. Spark is designed to efficiently scale up from one to many thousands of compute nodes. Correct? No? So it does not force you to use single tool. It can run over a variety of cluster managers. So Hadoop Yarn. So this is the first one, Hadoop Yarn. The most common choice when integrating with an existing Hadoop ecosystem. And second one is Apache Mesos. So a general purpose cluster resource manager it is. And what is the next one? Standalone scheduler. Next one is standalone scheduler. So a simpler cluster manager, including in Spark itself. So this is the easiest way to get started if you are setting up Spark on a set of empty machines. And the last one is Kubernetes. Okay. So the Kubernetes are nothing but what? Container orchestration tool of choices for modern cloud native applications. Guys, the flexibility here is a major strength. Correct? Now, if you already have a Yarn or Mesos cluster, you don't need to rebuild it. Spark can plug right in and use their resources. Very simple. Okay, so we now have a full picture of the Spark stack. Let's look at where we can apply this power. So look at here. So here all we can apply this power. Correct? No? Banking. So in banking, customer segmentation, credit risk assessment. So these are all perfect batch processing ML jobs, right? So targeted advertisement requires real-time analysis. And we have e-commerce. So clustering on streaming data for identifying trends. So as soon as trend emerges, Spark can update recommendations immediately. And next we have travel. Okay, the third one we have travel here. So travel provides personalized hotel recommendation, just like TripAdvisor. Maybe you have heard about TripAdvisor, right? So next we have media and entertainment. So this is automatic game complexity level setting by mining patterns in a real time or real time advertisement targeting. Guys, companies like Pinterest and Yahoo use this, guys. And healthcare, this is very, very important domain. So patients record analysis with past clinical data to proactively avoid hospitalization. So this is high impact predictive analytics, guys. And finally, we have fog computing or IoT. So sensors data analysis on the edge. So analyzing data near the source before sending it to the cloud. Guys, these example shows that any industry dealing with massive, varied, fast data can be benefited from this Spark. Correct, no? So, but Spark is not silver bullet, guys. We need to be aware of its limitations. So what are the limitations of this? Look at here. I have mentioned few limitations here. So when not to use Spark, that is very, very important one, right? Guys, no system is perfect. So despite its power, so there are scenarios where Spark might not be the best tool. High memory requirement. Suppose you have a high memory requirements. See, large batch processes with high memory requirement means, so there you are not supposed to use Spark. Guys, if your data size is consistently much larger than the total RAM in your cluster, so Spark will be the force to spill to disk constantly and losing its in-memory advantage. At that point, a disk optimized engine might perform better. And the second point is concurrency issue. Suppose you have a concurrency issue means, see, multi-user analysis environment where concurrent demand for memory is high. Guys, what I would like to say here is, since Spark relies heavily on RAM, many users running large memory intensive jobs at the same time can cause resource contention. Okay, and one more point I would like to tell you here, guys, scalability of concurrency. So it may not scale with the number of concurrent users. Guys, compared to the system designed purely for multi-tenant, high concurrency access, you're not supposed to use this Spark. Then what is the key takeaway here, guys? The takeaway here is that if your primary design constraint is high memory demand or very high concurrent user access to the same resources, you need to be careful, benchmark Spark against other specialized tools. Guys, with that understanding, let's wrap up our Spark introduction by going through the practical steps of getting started. That practical steps we are going to discuss in the next coming class, guys. Okay, so we have few practical steps. So this we can discussing in next coming class. Okay, is this clear? Thank you, guys. Actually, today I was a little bit fast, right? I was covering few theoretical concepts, so I was a little bit fast. Am I right, guys? So today I've covered so much of theory concept. Am I bored you? At the end, I'm asking you this question. Am I bored you, guys? So better you all go through the recordings, guys. Today I've discussed what so many important points are. So all points are very, very important for your examinations. And yes, see, the people are new to this Spark. So for them, it is very easy, guys. In assignment 1, the part 2 also needs to be done in group, right? Tushar, actually, no. See, I have mentioned. See, suppose the 4 member of your groups belongs to different organizations means, so then you go for individual projects. Okay. So if anybody is not belonging to organizations, otherwise they are non-technical, then go for group projects. So better always stick on to the individual projects for the part 2, guys. Okay. And as I told you, better take the recommendation letters from the company. Is this clear, Tushar? Okay. Guys, you have left with 16 days, right? So today is 2nd. You have left with 16 days. So 18th is the deadline to complete your assignment. So still you people are struggling with your group. So better you solve this very quickly, guys. So simply you are wasting time to frame your groups. See, we have announced long back to frame your own groups, but still you people are struggling with making groups. This is not fair, guys. This is the time to work together and to come out of the output, to come out with the output actually. Okay, guys, that's all about today's session. Actually, it is today I have taken 4 hours class. It is long class for me. Okay. Also, it is highly recommended to use OSHA portal, right? Yes, you have to use OSHA portal. Or can we use Docker in the local system? Also would work. Guys, what I would like to suggest is, see, OSHA portal is not yet ready. So you people, please go through the first part or second part of your assignment. So maybe yes, today or tomorrow. See, we are going to what check. So I am going to check personally. So whether all the tools are ready or not. So once it is ready, so I'm going to what send you announcement, guys. So today or tomorrow, I'm going to check the entire tools present on your OSHA portal. So once it is ready, then definitely I'm going to ask you to what give access to the OSHA portal. Okay. So maybe it is going to resolve in another 2 days, guys. They are wanting me to check the portal actually. Could you please share today's slides? So definitely. Samanvita, I'm sharing in Taxila and also I'm sharing the same in Microsoft Team, right? What link you are expecting, Ravi? Okay, you want me to ping OSHA portal? Don't you know the link? See, I have mentioned everything on your assignments, guys. You just go through the assignment I have given to you all. So in that Word document, I have given all. Yes, here. So one of my friend is asking this question. Pradeep, we are group assignments, sir. Then why we are encouraging for individual assignments, sir? Because all members from different background, some from cloud, tester, analyst, developer. Pradeep, already have told you, right? See, the first part of your assignment is a group project. Okay. The second part is situated learning. So what do you mean by situated learning? Situated learning means you people have to take the problem from your organization and then you have to use any big data ecosystem tools and then you have to solve. Okay, see here you are defining your own problem. See, you try to understand the importance of what the second situated learning. So why I'm giving that? That is for your purpose only, no? So that is benefits to you people only, no? So do we access the downloaded in OSHA portal if you want to download any data source? What is this? I'm not getting your question, Aditya. Do we access of download in OSHA portal if you want to download any data source? I'm not getting your question. In part 2, we would need to give demo on the POC created 1-to-1 or recording would work. Recording is work, guys. You just record the presentation and submit it. So it is not compulsory. So presentation is not compulsory. You just come out with the documentation. That is enough. Okay. So can we download anything in OSHA portal? what you have to download? Aditya, what you have to download from OSHA portal? Yeah, you can download. See, once you're connecting to OSHA portal, so it will show a normal system. So there you have a web browser. By using that web browser, you can download whatever you want. Yeah, you can sign to mail also. Part A, 4 members need to complete the problem individually. 4 docs, then combine them and share with you. No, part A, see, part A, it is a group project. Okay, so all 4 has to contribute each other, guys. So after that, you have to submit only one. So only one copy of your part A you have to submit. For part B, that is your situated learning. Individually, you have to solve and then you have to combine all and then you have to submit. So that information also I have given in your problem sheet. You just go through that. Yeah, sample data set you can download from OSHA portal. So can you show once in OSHA portal? What I want to show? Okay, let me do one thing. So instead of typing questions here, so let me allow you to talk with me. Yes, come on, guys. So now you can enable your mic and you can talk to me. Yes, somebody was asking question, right? Can you show once in OSHA portal? Do you want me to show OSHA portal? Ravi Kumar is asking this question. Ravi Kumar, you can talk to me now. You can enable your mic and you can talk to me.
Yeah, can you hear me now?
Yeah, Ravi Kumar. What I want to show you?
1 second. See, actually we are downloaded. Here in the course experiment, it is showing as BDS, CC, IPDP, NFC.
What you have downloaded?
Here 4 courses are there. It is getting echo?
No, your voice is clear, but I'm not getting you what you're saying.
No, just I'm trying to share. It is not disable the sharing option.
You're talking about what, Ravi Kumar? You're talking about data set?
Yeah. I'm talking about while going to the portal. It is showing in the course and experiment. It is multiple. It is 4 courses are there. Out of this, which one we need to do the practice that one?
Ravi Kumar, really, I'm not understanding what you're saying.
No. What I'm asking, once we are logged into that workshop portal,
Okay.
virtual lab, it is multiple things are there.
Okay.
Which one we need to do the start
BDS.
the control? No.
BDS is there, right? So
Yeah,
is my
BDS.
screen visible? Let me show you here. So is my screen visible to everyone?
Yeah.
So you are logging in. See, you're logging in like this, right? So immediately it will show big data systems V1, big data system V1. So here it is showing master node 1, node 2, right?
Correct.
Is this not visible for you people? These 3 nodes? This is visible, right?
No,
Ravi
for
Kumar.
me, no.
For you, no?
No.
Can you share your screenshot and chat box? It is showing BDS, right? BDS is nothing but big data. So
Okay.
BDS, big data system. See, master node, node 1 and node 2 it is showing.
Okay.
Correct, no? Ravi Kumar, already I've discussed with you, right? See, whatever the image they have provided for you people, it is not working. Okay, so today I'm going to check all the tools and I will ask them to give an access to you people. So can you wait for 2 more days?
Okay.
Yeah, it is not working properly because that is corrupted. So that's why I'm checking, guys. So even parallelly, I'm working on that. So today I'm going to check all the tools. So once everything is working fine, then I will ask them to what? Share with you people. Is this okay? You may only have one AWS course instances running at a time. So please stop the current instances before starting a new one.
Yeah, that's fine. I clicked some other one. Now again I clicked that BDS master data. It is saying that message.
So once your work is over, you have to stop this. That is very, very important. Okay.
Yeah,
So
and one
because we
more
have
thing,
allocated
for
time
the
here.
exam, we need to write the exam in center or in online. Is there any option?
No, you have to write in centers.
Center only. Actually, when I'm selected that Miapur location that is in Hyderabad, it is showing very far, more than hour.
Regarding this, you discuss with the operational team, Ravi Kumar. So you
Okay.
have exam team, right? Support team. You discuss with them. You just type support. You'll get a mail ID. You text to them. Okay, you mailed them. They will help
Can
you.
you ping here? I will write.
Support. Something you have to type here. Support. Yeah, support VBox, not VBox. Exam platform support.
Please ping me in the chat group. I will take it.
Wait a minute. I will share with you people. I have taken that in course. Yeah. Support at wilp dot. This is the mail ID you have to use. See, operation related queries, exam related queries means you have to mail to this mail ID. Okay. Support at wilp.bitspilani.ac.in. Ravi Kumar, have you accessed? I have pasted in chat box.
Yeah, thank you. Thank you very much. I've
Yeah,
seen
thank
that
you.
one.
Yeah. Jyoti, yes. What queries? You can enable your mic. You can talk to me, Jyoti.
Hello.
Yes, Jyoti. Your voice is audible.
Yes, sir. Actually, yeah, while doing the BDS lab, actually, I think I forgot to stop the session. So I think I adjusted the time limit. So